speakers, Mehmet and Gulian, who's going to talk about some optimization techniques with his work, his collaborators at Sandia. Take it away.
Thank you. So I'll be talking about our paper, A Block Coordinate Descent Optimizer for Classification Problems Exploiting Convexity. And this is a joint work with Ravi Patel, Nat Trask, myself, and Eric Sear. We're all at the Center for Computing Research at Sandia National Labs in New Mexico. So our motivation for doing this work is to explore feasible and smart ways to use second-order optimization techniques. So these hold intriguing potential for deep learning. As mathematicians, we're drawn to them, but second-order optimizers scale prohibitively with the huge number of parameters in deep learning, and they also are very sensitive to the type of loss surface that you have, and particularly if you have a very non-convex, very complex loss surface, it may not be worth it to use a second order method. And for that reason, people in deep learning have stayed away from them, and the state of the art for classification is all using first order gradient based approaches. So we introduced a coordinate descent method to train deep neural networks for classification. And if you don't know what coordinate descent is, that's just optimization where you separate your variables into two disjoint sets, and you alternate between updating each set. And our partition exploits global convexity of the cross entropy loss with respect to the weights of the linear layer. And it makes it worth it to do a second order method on that set of variables. So we alternate between a second order method to find the globally optimal linear layer weights for our deep network, and just a first order gradient descent method to update the hidden layer weights. And I'll explain this more, but it ensures an optimal fit of the basis that's encoded in the network to the data during the training. The other advantage here is that the Hessian in the second order step scales only with the number of weights in the linear layer, and it doesn't grow with the depth and the width of the hidden layer. And that also means that our method is agnostic with respect to whatever hidden layer architecture you have. The results that we show an improvement of a few percentage points in validation error for some benchmark classification data sets. And we also demonstrate a surprising, striking qualitative difference in the basis functions that are encoded in the hidden layer. So let's just review the architecture for classification problems. Here I've written out the loss for a classification problem. And in classification, you have an input X, and you're trying to decide which class Y it belongs to. So if we just look at this architecture, the first three things here are the actual neural network. You have the hidden layer, the linear layer at the end of the hidden layer, and then since we're doing classification, we have softmax, which maps the output of the linear layer. The linear layer output can be basically arbitrary, but softmax turns that into probabilities, and then the cross entropy loss is the last component we need. The linear layer is parametrized by the weights W, and C is all the parameters for the hidden layer, so the weights and biases there. And the hidden layer can basically be anything. It can be dense, convolutional, and so on. These are the formulas for the different layers. I assume you're familiar with this. And these are the dimensions. So the hidden layer goes from the input dimension to the dimension of the linear layer, which we call n basis. You'll see why. And then the linear layer maps that to the number of classes, and then the softmax turns that into probabilities for each class. So why do we refer to the number of nodes in the final hidden layer as n sub basis? This is motivated by our previous work, which was done with Mauro Perego, who's also at Sandia. This paper was called Robust Training and Initialization of Deep Neural Networks, an Adaptive Basis Approach. And the idea here was that we applied a similar coordinate descent method for regression problems. So your architecture in regression looks like this. If your function that you're approximating is univariate, you have your hidden layers here, and then the linear layers, which turn it into a scalar valued function here. And if you just denote the output of your vector valued hidden layer, the final one, as phi1, phi2, and so on, then you can write the output of your neural network like this, which exposes that the output is linear with respect to the linear parameter weights, but that these phis you can think of as an adaptive basis function, adaptive basis functions that depend on your hidden layer weights. And so, because also the loss function in regression is a least squares loss, you can actually, for fixed hidden layer weights, you can find the globally optimal linear weights in a single least square solve. So again, instead of just doing a gradient descent method, a standard gradient descent method, you always update and evaluate and update your hidden layer weights using gradient descent, using the optimal representation of your adaptive basis, the optimal representation of your data in that adaptive basis. And what we're trying to do here is trying to apply a similar method for classification. Now, the issue with classification is that the output of your network is no longer linear in the linear layer weights because you have that softmax, and the final part of the loss, the cross entropy, isn't the least squares thing. So you can't get the globally optimal linear weights in your network in one shot, but you can show that your loss function, if you freeze the hidden layer weights, is still convex with respect to W. So there's a global minimizer, and you can expect to find it using a Newton search. And that's the basis for this coordinate descent. We alternate between doing a Newton solve to get the optimal weights given the hidden layer parameters, and then we update the hidden layer parameters with a step of gradient descent. Now, like I said, our reason for this is we don't want our Newton, if we hit the whole thing with a Newton method, that would scale with the total number of parameters, which would be too expensive for a second order method. But now the Newton method step will only scale with respect to the number of basis functions. So the width of the linear layer times the number of classes, which we think of as fixed. So we use a Newton method with a backtracking or trust region. If you do this right, you can expect to get a global minimizer. And the details are in our paper, but we find the step direction from Newton and then keep reducing it until we satisfy keep reducing the step size until we satisfy the Armijo condition. And for the gradient descent part, for the hidden layers, we apply Atom. Since we're doing image classification, our data sets are pretty large, so we do stochastic gradient descent. So we do batching in Atom. That means that, so there's this caveat that since we're doing batching, when we're doing our Newton step over that batch, that the parameters are optimized. We have the optimal representation of that specific batch in our linear weights. So our first benchmark is the peaks benchmark. And this is a simple two-dimensional classification. It's not really an image classification benchmark yet. This is from a paper by Haber et al. And this allows you to visualize what your classification algorithm is doing. So the setup here is that we just have a scattered point cloud. So we're in the unit square, and each point is assigned a class, and we have some finite sampling of that. That scattered point cloud is our data, and we have another separate point cloud that's consistent with the partition of space. That's our test set. So I'll explain what's happening on these pictures on the right in the next step, but we train depth 4 dense networks with input dimension 2, obviously, and we have 3 hidden layers of width 12 that contract to a final hidden layer of width 6, and we use Tanch activation and batch normalization. We sample 5,000 points here, And the NGD, the Newton gradient descent, uses 5 Newton iterations per training step, with 3 CG iterations for the linear solve. And the learning rate for Atom for both Newton gradient descent and standard gradient descent is 10 to the minus 4. So the black curve here represents, this is training and this is training and this is validation. Left is training, right is validation. The black curve is just standard Newton the red curve is standard gradient descent and the black curve is Newton gradient descent. So you can see that the Newton gradient descent gets to a good accuracy much faster than the regular gradient descent. And you get a similar training accuracy, but when you look at the generalization error, when you look at the validation, you get a few percentage points increase in the Newton gradient descent approach. This is all averaged over 16 independent runs, and the shaded areas are the mean plus or minus the 1 standard deviation. So what does a gain of a few percentage points look like, since we can visualize what's actually happening here? So this is the final prediction of the classes using gradient descent, and this is the final prediction of the classes using Newton gradient descent. And if you compare it to the training data, you can see that although a few percentage points doesn't sound like much, you actually get a much better recovery of your classes using Newton gradient descent. So for example, you have this artifact here with gradient descent that you don't have. You also have some sharper corners and some wiggliness in these boundaries that you don't have with Newton gradient descent. And it's so that's what a difference of 1.3 accuracy looks like. And something remarkable here is the difference in the basis functions. So these are simply plots of phi1, phi2, phi3, phi4, phi5, and phi6. That's what these basis functions are. You put these into a softmax to get your classes. But the basis functions in Newton gradient descent are much more regular, and whereas in gradient descent they're sharp, and you can interpret this as saying these functions have to give you a good recovery to the data using a poor, suboptimal choice of coefficients in the linear layer. So they sort of have to fit to the classes already, whereas the Newton gradient descent, since you're gaining much more accuracy using optimal choices for the linear layer weights, you're not demanding as much from your basis functions, and you can still recover the classes better than you can using gradient descent. So then we looked at some standard image recognition benchmarks, some of the simpler image recognition benchmarks, MNIST, Fashion MNIST, and CFAR 10. So for MNIST and Fashion MNIST, we just have a simple dense network. We use simple dense networks for the hidden layer. For CFAR 10, we use convolutional architectures. The details are in our paper, what specific architecture, but this illustrates that you can apply this strategy with whatever hidden layer architecture you want. So as another caveat here, if you want to get state-of-the-art results with these different benchmarks, you need to do things like data augmentation and all kinds of hyperparameter optimization and tuning the architecture. But we don't consider all these tricks. We just want a simple comparison of, standard dense networks or convnets with gradient descent versus and Newton gradient descent. So for all the results that I'm going to show you, with these simple architectures, we optimize the hyperparameters using GP optimization and scikit-learn. And we actually partition the data into 3 sets: a training set, a validation set that we use in the outer loop of our hyperparameter optimization, and then a final, what did we call this? I forget, but then a final test set where we test our hyperparameter optimized setups that have never seen this last data set. So the story is in terms of the training accuracy and the validation accuracy is sort of similar to what we saw in the peaks. You basically never do worse with Newton gradient descent. You converge faster. You never do worse than regular gradient descent, and occasionally you get a few percent increase in your validation accuracy. So, like I said, these aren't state of the results for these benchmarks, but my understanding of the image recognition world is that they have lots of tricks. This data augmentation trick, this architecture trick that gains them a few percents each time, and stacking these together, they can get a state-of-the-art result. So these results suggest that this might be a useful tool in that, a useful item in that toolkit for squeezing out a little bit more accuracy out of your architecture. So the conclusion here is that this Newton gradient descent method is motivated by this adaptive basis approach to training neural networks. It's a block coordinate descent method for classification problems that is a hybrid. It's like a 1.5 order method. It's second order in the linear weights and first order in all the other weights and biases of your network. It exploits the convexity of the cross entropy loss with respect to the linear layer variables. And it uses a Newton method to get the global minimum for a given batch of data before doing a step of gradient descent and then alternating. So we demonstrate that it accelerates training, and it can give you, typically between 1% and 3% improvement in the final validation accuracy. And looking at the basis functions in a low dimensional example shows that there's a big difference between Newton gradient descent and just standard stochastic gradient descent and all the variables as far as exploring the parameter space corresponding to your hidden layer variables. So I'd like to thank the organizers for inviting us, and I'd like to thank you for your attention. These are our grants that supported this work. And with that, I'll take your questions.
Thanks a lot. You're right on time. We've got 2 minutes for any questions. So I had one, just anytime I see these sort of inner outer loops or partitioned optimization, are there games you can play or guidance for the tolerances and the over solving or under solving some of the Newton part of the algorithm and then the linear part of the Newton algorithm? Did you see any of that?
So there's a regularization parameter. I'm trying to remember if we sort of found if we found strong patterns in our hyperparameters, or whether we just let them, let the Gaussian process optimizer do whatever it wanted.
Mamikon, for this one, if you take too many iterations in the Newton step, it'll overfit. So a lot of these are like 3 or 4. It's just a handful of Newton steps, which is enough to help things out. But otherwise, you do run into overfitting, which is kind of the pathological part of classification.
So did we enforce a small number of Newton steps, or did the optimizer just find that on its own?
I think that was a trainable parameter.
Yeah.
Trainable hyperparameter.
Okay, so that's kind of the general guidance is don't oversolve, and then that should be treated as a hyperparameter. Okay.
Sort of an implicit regularization that it's doing.
Okay. Well, thanks. Yeah, so please follow up. I think Matt volunteered to answer questions, but as stuff comes up, please just post it. And if people can answer in the chat or connect later, since there's such a tight schedule. Okay, thanks. Mamikon,